So no longer logging any native forests, that's state forests, national parks and state parks. And the reforestation program, which could be in conjunction with the selective logging program, is to actually build our forests out. That's a way of drawing carbon down. Where we've cleared the forests many years ago, we can regrow and we can create biodiversity links through the landscape. And actually, if we don't hit the mark and we do get a step change in climate, our flora and fauna can move through the landscape and we don't have mass extinctions. So we can rebuild that in a way that creates resiliency. And agrichar, biochar, very important. Known as terra preta de Indio, it was what the Amazon people used to replenish and create nutrient-rich soils in the Amazon basin. And they were able to use a process called pyrolysis, which is cooking up wood, and then it removes all the energy value from the wood, and you end up with this very porous char. They put it in soils, and then the soils look very black, and they're actually able to retain like nitrates and retain water, so that you get much higher yields in those soils. So we can actually bring back our farming with agrichar while also drawing down atmospheric carbon, and that's really the big part of carbon debt, is probably going to be serviced by drawing carbon out of the atmosphere into farm soils using char. So we've all heard about inventing a coal solution. The big one in the US failed. I think the US DOE have pretty much abandoned it. Obama's not on message with clean coal. We heard of a new kind of clean coal called the Callide oxy-fuel process, launched by Martin Ferguson the other day. Well, you know, it's a new one every time one fails, and it's all about marketing coal and about extending the life of our exports. So here's the latest one I offer you. That's the latest clean coal, and hopefully it's working in about 10 or 15 years and it's going to save the planet. But I'd argue that if we look below that, and we've got real solar thermal farms, and these take light in on those mirrors, reflect it onto the absorber at the top, and create superheated steam to drive turbines and create electricity. So we need an approach to get to 300 parts per million, looking at fast rail, urban rail, rail where we've got buses, solar thermal farms, wind farms, and rooftop solar PV, things like that, and of course energy efficiency. So baseload solar thermal, you'd be amazed at the number of approaches to solar technology. We've got governments funding, we've got private individuals funding, we've got private corporations funding different technologies. We've got conventional parabolic troughs, and I'll tell you a bit about them in a sec. They've been around for a long time. We've got solar power towers, where a whole lot of mirrors in a field reflect light up on a tower. We've got solar dishes, where that's from ANU, where they reflect light onto the head of the dish and they get the hottest temperature steam from that process. We've got really cheap options like Australian-designed compact linear Fresnel solar power. We've got the Europeans doing a similar thing with linear Fresnel. And Fresnel lenses, which are effectively a flat representation of the dish above. So all these are just a small number of innovations in the solar area. And you know, I'd be here for 5 or 6 hours if I showed you all the ones that are out there. So back in 1912 to 1913, Frank Schumann actually, with the support of the German government, set about irrigating the desert in Egypt. And he had his first plant up and running, and he was pumping 22,000 litres a minute from the Nile to irrigate cotton fields. Unfortunately, World War I came. He fled back to the United States, and his parabolic trough plant got destroyed. And what happened next is they found oil gushing from Arabian deserts, and they thought that was an easier way to get heat, or they just didn't notice the old method, and so that didn't get another look in. So effectively, if World War I didn't break out, they would have been building these solar arrays, and then everyone would have seen the potential, and that would have evolved into our energy future. And what was he doing? Well, he was looking at this 8-inch deep layer of oil that we get annually. And the 8-inch deep layer of oil is effectively the amount of energy that the sun casts upon the earth each year. That's 100,000 terawatt hours. And humans in 2050, according to the IEA, and I don't always agree with them because they always go for the bigger number because they want to create space for their fossil fuel industry, they say we'll only need 15 in 2050. So we get 100,000 terawatt hours. The Three Gorges Dam in China, one of the biggest renewable energy project in the world. 25 years of engineering, massive, 630 square kilometre reservoir system, and now it's all silting up. It's become a bit of a disaster. They moved on 1.3 million people. They're moving on more now because of the silting. Well, that yellow, take note of that yellow square there, because concentrating solar power would generate 1.7 times the power in the same land area at significant lower capital cost and faster construction time. The Hoover Dam. What would it take? That little blue dot down the bottom of solar thermal would produce the same amount of power as the Hoover Dam, and again, it would come in much cheaper. In Spain, they're building these mirror fields that reflect sun onto power towers. They're building them with storage so that they can dispatch power when we need it after the sun goes down. But unlike our coal plants, they don't dispatch power at 3 a.m, whether we like it or not, whether we don't need it. Google's in on the act. They've got their own version of solar power towers that they're rolling out, and they're planning to provide their whole company's electricity consumption. It's one of the biggest consumers in the United States with renewable energy. There's some more pictures of the Google technology. This is a trough plant, the same as what was built in Egypt in the desert, and put online by a company that operates here in Australia, Acciona, in 2007. They built that, demonstrated it, and proved the cost. And this another parabolic trough plant. Just 2 months ago, they got 7.5 hours storage online. So after the sun goes down, they can provide 7.5 hours of power, the equivalent constant output. And that's enough to ride through the night, because we don't need full output in the middle of the night. Then we've got the Australian company, and I'll show you a little bit in depth about this one. It's Ozra. This plant's at the Liddell power plant, and these mirrors, linear mirrors, reflect light up on that top absorber, and that's where water is pumped through there, creates steam, and they drive turbines. So this is how it works. The sun comes in, hits the reflectors, which are all angled slightly differently so that the light hits the absorber. They can make these panels in factories really cheaply. We can build those factories in the Latrobe Valley or where coal communities need a just transition. The compact linear Fresnel manufacturing process and rollout is quite simple. Here's a forklift just loading up the reflectors onto the framing. The benefits are sturdy and low-cost construction. Primary components are steel, glass and water. This goes for all the technologies. Efficient use of land. Air-cooled, so minimal water use just for cleaning. No toxic materials, unlike coal power or nuclear power generation. Easily protected from hail and dust storms, they just turn over. Can be hybridised with fossil fuel plants. Not something we need to bother with. And there's a few more photos there. So here's sun incidence in Australia. You can see 11 hours in the top left-hand corner. And you can see in north of Victoria at about 6 hours. So what could we do? We could put solar thermal plants in these locations, providing power into Melbourne, into Adelaide. The grid's all joined together except for the Perth grid, which is on its own. Moree's a great location to provide power to Brisbane and Sydney. So here's some modelling Ozra did, and they said they could supply 91% of the eastern seaboard's power by discarding 10% of the power. So that means in summer they end up with a little bit too much power, and having 17 hours of storage. So that means in order to ride out all the modelled weather conditions and cloud that's overcast, and to ride out long nights in winter, 17 hours of storage. And you can see there at the bottom they've got the solar incidence that they throw away. They don't throw any of it away in the middle of winter, and the red line shows you the solar capacity. So effectively, with a bit of boost in winter, which can be provided by wind power, because you'll see a correlation: when there's less sun, there's more wind, and by having the storage available with solar, when wind incidence is down, the solar thermal with storage can take up the slack. So we've got a base load power system, one that delivers power when we need it, dispatchable. So we need to electrify our passenger